Yeah. So as I said, today we are just going to do a few examples on problems involving uh, displacement time graphs, displacement time graphs, and velocity time graphs. All right, we're going to work a problem or two, yeah, maybe one or two that might involve even the equations and so too. All right, we'll have a short class. In preparation for, and I'll probably have to put up a notice somewhere in the maybe in the group or Moodle or both, because next Tuesday we're gonna have a little assessment. I think the course outline says you have to do 5 of them, so we probably can do one Tuesday. 10% is it of your overall course grade, right? So start preparing for that. It's going to be based on everything we did so far, right? I haven't finalized yet. Usually, when I do an assessment, just to add a layer of security, I would usually have students join Zoom on their phone and do the assessment on their computer. But it's a big group. It's too big a group. When I did big classes like these, usually what we do is split them up, you know. And you say maybe okay from well, it's going to be a short something, right? Maybe it's not going to be longer than it can be longer than half hour, right? Can be longer than half hour. It's going to be very short. Um, and I usually split the class up. If it's a well, this class is about 100 and something. I think that's what I saw somewhere in Moodle or one of the days I saw a big number of students joining the class. So I might split up the class, maybe all those whose names, their last name is starting with A to maybe, uh, maybe A to what? G, and then G from G to something, and then from that to Z. So you don't have a big group doing the quiz at the same time. So I break it up into 3 manageable groups so I can see what's going on. Um, I want to make sure that, the assessment is transparent, it has integrity. Last year I had to write a report for a particular group. Some things the institute is very strict with those things. All right, good. So let me start with a nice little okay, look at this problem here. One second. So I think everybody should see that, right? Everybody seeing this? So the problem involves two buses, right? Well, this textbook was written in England, right? So that's why they're going to use those names there. So one bus is coming from Birmingham. It leaves at 9 a.m. It's traveling at 60 km per hour. And another bus a little later leaves Rugby at 9:15, and it's going towards Birmingham instead, right? And it's traveling at 50 km per hour. And they're asking how far are they from Birmingham when they pass, right? So uh, that's our little problem, right? Good. So how do we handle this? Thinking if I could have made this a little smaller. Good. So as I said, we're going to make use of a graphical approach to solve such a problem, right? And let me borrow the solution that the book gives that uh, what I mean, copy. All right. All right. That's not it. What's happening there? Paste. No, there's pasting the same thing. What's going on here? Control V. Oh, that's it. All right. So far, this thing is. Uh, oh, the whole thing is moving. Oh gosh. I wanted this to be. Let me see if I can bring it close by. Yeah, that's what I want. All right. Sorry about all of that, right? I guess that was uh, messing with your eyes and all of that. Good. So as you can see here, right? The first bus leaves at 9. Okay, so here, let's call this maybe let's call this here. Let's say this is Birmingham, right? Birmingham. Good. That's here. And it starts at 9, right? And what is it doing? It's doing a speed of 60 km per hour, right? So how do you represent that? How do you represent that? um, on a graph? Well, in 1 hour, notice 9 a.m. is here, 10 a.m. is here. So you expect that it will cover 60 km in that 1 hour, right? So that's how you'll draw it, right? Because you might wonder where these people got this graph from. So if the train isn't a train, it's a bus, it's traveling at 60 km, well then in 1 hour from 9 to 10, it should cover 60 km, right? Good. So that's this line is definitely that bus from Birmingham to what's the place name? Rugby, right? Good. And the next one says moves from, it leaves Rugby at 9:15. So we want to think, don't worry with this piece of the graph. Don't worry with this piece. They just project the line here, right? So where 48 is, right? Where 48 is, that bus leaves Rugby, right? Rugby. And it's moving at what, 50 km per hour, right? 50 km per hour. So in other words, 50 km, let's see, all right. So in half hour, that's from here to here, it should travel 25 km. So 45, 48, and take away 25 will be what? 25. So here is going to be like
Sir, 23.
23. Yeah. Right? So you plot these 2 points, right, in half hour, and that's the kind of reasoning you got to put in, right? In half hour, it's going to actually travel in half hour, in half hour, it will travel 25 km, right? And if you start here, you'd have to check 25 going this way, and that will bring you to 23 here, right? And that's your second point. And you just draw a straight line through. And all you got to do now is where they intersect there, that's your time, right? Well, of course, this graph it doesn't give you all the finer details. But the answer is actually 9:33 a.m. Right? It's 9:33 a.m. If you have a nice graph paper, if you have a nice graph paper, well, you'll be able to see that this finer point, right? You'll be able to see that this is 9:33, and you'll be able to see, well, at what distance, and you'll actually be able to read off here as 33 km, 33 km from Birmingham, right? If I give you something like this, well, you can't draw the graph. Your thing will basically be multiple choice or a short answer or what, right? So I might have to very well give you a couple of graphs and say, which one of these graphs describe the journey of the two buses, right? And all you have to do is pick out which one. So yeah, this is a graphical approach to solving such a problem. Of course, you can calculate. You could calculate the answer. It's going to be a little more complex to do. The graphical approach is very simple, right? We got to know the draw graph, right? And you saw the reasoning, right? If this first bus is going at 60 km per hour and starts at 9 o'clock, right? Just to get the graph, even though they're going to meet up if they're going to meet up somewhere here, and if the distance between the two places is 48, notice the graph has up to 60 here, and they actually go up to 10 a.m. there, just to get an idea of what the graph looks like, right? So in 1 hour from 9 to 10, this first bus is going to travel 60 km, right? So you start off here at zero, at the origin here at 9 o'clock, and you will cover in 1 hour 60 km. So you draw a straight line through there, right? Just to represent that bus, because nothing says that, well, yeah, I mean, it's true that they're traveling and they're going to pass each other and so, but they can go on traveling as well to other places, right? But let's just leave that. And then for the other one, which is a little more tricky, right? You can't start here. You have to start from somewhere up here, and you're going in opposite direction, right? So at 9:15, this one is starting at 48 because Rugby is 48 km away from Birmingham, right? This projected piece here, well, it's just to, this extra piece here is just to give you a sense of the graph of the distance time graph of that particular bus. But this is the piece that's going to help you to draw the graph, right? It starts at 9:15. So from 9:15 to 9:45, it should cover a distance from 48 to 23 is 25 km. Because the bus is traveling at 50 km per hour. In 1 hour, it'll cover 50 km. So in half hour, it's going to cover 25 km. And what we see here is where they intersect. That's what you're interested in. You can read off the time. You can read off the distance, right? And since Birmingham is used as the reference, well, you're going to measure from there to where they meet up, right? Which is 33 here. The detail is not very clear on this graph, but as I said, if I am to give you something like this, I'm going to give you a graph with sufficient details that you can read off that point accurately. Fair enough?
Fair enough.
Yeah. All right. Let me give you another one. Let's do another. Oh, what's happening there? So I have to erase all of this. Oh my. I think I used the wrong thing to write with. We're going to another one that involves a displacement time graph. Okay, good. So, all right, let's say what's going on here? Yeah. Let's say you have some information that gives you distance and time on some kind of table. You know, the table, well, not always you have to draw, all the, the division and so you don't have to do it. Yeah. And remember, again, you might be saying, wait, we're not doing displacement time graphs. But remember that I said when you're dealing with a straight line movement, more motion in one dimension, we sometimes can use the words distance and displacement interchangeably, right? Not always. Good. So let's say we want to draw this graph. We want to draw this graph. And perhaps they ask, well, what? Calculate, determine, um, the velocity. Velocity. As I said, if it's a straight line, it's the same. You can ask for the speed, right? Of the body. Good. So let me bring the graph over. Uh-uh. For some reason, this whiteboard not behaving the way it usually behaves. For some reason, I wonder why. Nope. I may have to switch to a um, it's not happening, man. What is going on here? All right, let me just stop sharing for a moment. Just give me a sec. Yeah, sorry about that delay. The whiteboard was misbehaving. Huh. Yeah. So here's a distance time, some distance time information for a body, right? And that's what the graph look like. As I said, there are times when we can actually use distance and displacement interchangeably if we're dealing with movement in one direction, right? So since there's no change in direction, we're dealing with a single direction, as in one-dimensional motion. Well, then the two can be used like that, right? Good. Um, Here's what the graph will look like, right? And you can see the points. 0, 0, well, that's this point here, right? That's this point here. 2, 1, right? So the time is 1, distance is 2. At 2 seconds, the thing is 4 meters away from the starting point. At 3 seconds, the thing is 6 meters, and so on, right? So if from this um, graph here, if you're required to find the velocity, what did we say is the velocity, or how you can get the velocity when you have what you call a displacement time graph or a distance time graph, because we're moving in one direction? Anybody can remember?
Sir, is U equal U, which is initial velocity, equals acceleration time?
No,
If I'm
no,
right?
we're not using the equations here.
Okay.
We're using the graph, and I
Oh,
think
the graph.
I said something. I was telling you all about making notes and so, and I y'all
Sorry,
remember that?
Ryan, you could find by calculating the slope or the gradient.
Very good. That's it. That's it. Right? So since this is a straight line, the slope is going to be the same everywhere. So you can take any 2 points, right? Any 2 points, right? I'm just going to randomly take, all right, I can take here 1, 2, and let's say take this one here, 4, 8, right? And your velocity is going to be equal to 8 minus 2, 8 minus 2 over 4 minus 1, right? And you'll get, what's that? 6 over 3, which is 2, right? And your unit will be meter per second, right? Simple as that.
Sir, I also used a calculus method and I got 2 as well.
Okay. All right. Use anything you want, but yeah. Just for those who don't know, right? If you have a graph, right? If you have a graph, and maybe let me just mention that because it might not be clear to everyone. I think I'd have to erase all of this before I proceed. Let me see. New slide. There we go. Yes, I have to. I'd have to erase all of that. Before I move on. For those who don't know how to find the gradient of a graph, let me just share this bit with you. Very important. So if you have a straight line graph, right? You have a straight line graph, take any 2 points, right? So if down here is x1 and down here is y1 and down here is x2 and down here is y2, right? So the coordinates here is x1, y1. Coordinates here is x2, y2, right? And you have to find the gradient of this line. Basically, if you take these 2 points, it's like you're finding the tangent of this angle here, right? So gradient equal to y2 minus y1 over x2 minus x1. It's also the same as y1 minus y2 over x1 minus x2, right? It's the same thing. You'll get the answer. If you're taking notes or what, you can take it. Of course, I'm recording there, right? So you will see it again. So once you have a straight line, that's how you find the gradient. And why I'm showing you this is that we said that the gradient of the displacement time graph is the velocity. And therefore, you need to know how to calculate a gradient. Okay, you might be very well asked that. You're going to be asked that. I'm going a little slow because the mathematics, as I said the last time, I am having trouble knowing what's the level I should be at. I'm not sure. I'll know by next Tuesday when I give you the little test. I'll know where you're at. Yeah. Um, so I'm gonna remove this because I wanna use a curve. If you do have a curve now, what happens? let's say you have, as I said, you can have a displacement time graph that's a curve. All right, let me make the curve more pronounced. Maybe like that, you know? And you want to know the instantaneous velocity at this point here, right? You want to know what's the velocity here, at this exact point, P. Now again, I might have to give you a graph, right? And the instantaneous velocity at this point is going to be the gradient of this tangent. So you have to draw a tangent here. Draw a tangent that touches direct at P. And that's always a tedious thing, right? And when you draw this tangent, you'll have to locate 2 points in it. 2 points in it. Take this point here, take that point there, right? So let's say at this point you have x1, y1, and down here you have x2, y2, right? And the gradient at P is equals to gradient of tangent at P, right? Which is equals to y2 minus y1 over x2 minus x1, right? You can turn it around the other way too, no problem. y1 minus y2 over x1 minus x2. So when you have a curve, remember the gradient is different at every point. With the previous example where we're dealing with a straight line, the gradient is the same everywhere. So you just do one calculation, you're done. But with this curve, at every single point, the gradient changes. So to find the gradient at a particular point, what you call instantaneous velocity, you'd have to draw a tangent. Of course, you can't do that. I can't give you a question where you have to draw a tangent, unless you're doing a face-to-face exam and you have the paper and so. It's always difficult. Look, I work with CXC and they would send the question paper to me to moderate, right? So I have to work out all the questions and so. And when I have to do drawings on their graph, if you see the thing condition, I can't do it. Because how do you draw on the computer screen, you know? There are tools that you can use, but I don't have them. And I can't invest money in tools that, well, if the money CXC is going to give me doesn't, you know, compensate, right? There are special tools you can use, but I don't have it. So I would draw with my hand, man. I get all kinds of things on this little drawing pad that I have here. Right? But I will have to give you the graph. I'll have to draw the tangent for you. It's like I'm doing everything for you, man. But you will have to do the calculation, right? You will have to find the point. The points, like this point here, you'll have to find a suitable point, find another suitable point, right? You get this, right? Good. So you can also from this graph, you can also from this graph, let's say, oh my. All right, all right. Let's say you have a similar graph and you want to know the average acceleration between x1 and x2. Sorry, not average acceleration, average velocity. So what you do, okay, draw up here, draw across, y1, draw up here, draw across, y2. If you want the average velocity, well, as I said, we'll use them interchangeably. You draw a secant, they call it. You connect here and here. So you draw a straight line straight through. Oh my, oh my, oh my. I just told you about my problem with drawing on this thing. It's not easy for me. Yeah, let me see if I can. Second go at it. Ooh, yes, yes, yes. It happened. So you draw this secant and the gradient of this secant here, right? Is secant line, secant, right? The gradient, average velocity, average, let me erase all of this and write it properly. Average velocity equal gradient of secant, right? Which is that. So again, this point here is x1, y1, and this point here is x2, y2, right? So you have to pick out those 2 points, read them off, and do this calculation. So when you have a curve, well, that's your big problem. So we okay there? All right. So let's switch our attention a little to maybe a velocity time graph. So let's see problem that involve a velocity time graph. All right. Let me borrow one from here. What's happening here? One second. These things take some time, eh? All right, good. So here we have some data, right? Let's plot that on a graph, see what it looks like. Okay. That's what it looked like, right? You can see there? So we have some data, and here it is. We have a straight line graph, right? What should we get from this straight line graph as to the acceleration of this body?
The gradient.
Yes, and what about the gradient? What about a gradient? Anything special? This is a straight line. What is peculiar to the gradient of a straight line?
Any point on the straight line supposed to be the same gradient.
Very good. That's the point. Yes. And therefore, if the gradient is the acceleration, then the acceleration is constant everywhere, right? And this is an example of what we call constant acceleration, right? Because the gradient is the same. Throughout this line, it has the same slope. So this thing is moving with what we call uniform acceleration. And we can calculate it by calculating the gradient, right? So if you want to race me to calculate it, that would be nice, right? So maybe I'll take a point. All right, I can take the origin here, 0, 0. And then maybe I can take the biggest point here. What is this? 520, right? So acceleration then is equal to 20 minus 0 over 5 minus 0, which is 4 meter per second square, right? If you want to write it as meter per second square, that's up to you. So the acceleration is equal to the gradient of this graph. I like that, right? Good. So let's say you want to know the distance traveled by this body. How do you figure that out?
They're the total area.
Good. So how we calculate that? It's the area under here, right? This area here.
Since it's a
So-
triangle, we can use breadth times height all upon 2.
Yeah, great. Yeah. Distance traveled is equals to half, what's it, base time height? Half of the base, which is 5, times, what is it, 20, right? Which is what, half by 20 is 10, 10 by 5 is 50 meters. Right, so that's this area under here. It's a triangle. It's a triangle, right? This area here. Not very difficult, right? So we can get from the velocity time graph, we can get the acceleration and we can get the distance traveled. These days they have these software, that you can feed in data, and it can tell you a whole lot. I was teaching. UG has started, or they have brought the engineering students to Borbies. Those who belong to Borbies can now attend classes in Borbies. So they have me teaching a few students who are doing physics course too, right? And I was showing students that, look, well, I think those students were mechanical engineers, I think they said. Well, I mean, they're students who are, reading for a mechanical engineering degree. And I was showing them how, when you have a velocity time graph, maybe I should do what? If I do this new slide. Oh, it's going to have all of this on it. Oh my. Yeah. All right. One moment. Yeah, I'm going to erase all of this one. Yeah, for them, let's say they're looking at a car engine, you know, and or some kind of engine. And if their displacement time graph, sorry, their velocity time graph is maybe like this, you know. And I was showing them that, okay, maybe for the first 10 seconds, the vehicle can barely go up to 20 km, let's say km per hour, right? Yeah, let's just say that, 10 seconds. Yeah, you can have that. So people would say this is a slow pickup speed, right? And I was explaining to them that they had a car racing in Kanji here, Berbice. People come from all over. And guess which car beat them up? An electric car, because the electric car doesn't take so long to pick up. An electric car can probably move from 0 to 60 in 10 seconds. It's much steeper, you know. Sorry, I should put a 60 up here, maybe 60 here, right? In 10 seconds, 60 up here. It's much, it picks up very fast. And there's where this kind of graphing can help them to see, well, where is it, you know, okay, for the first 10 seconds, we got to do something about, you know, the engine's pickup speed and how they can improve it and so. Right? They that kind of, they have instruments that would do all of this for engines, for all kinds of things. Right? They can make use of this sort of thing much more than us, you know. Yeah, back to, let's take another question. Let's take this one. Okay, so look at this one. Let me see if I can make it smaller, because I have to fit a whole big graph here. Yeah. So here, the journey of a train is described in, you know, greater detail. It's not like the train is traveling at a constant speed and that's it. No. For the first 10 seconds, you notice, right? For the first 10 seconds, it's moving at 0.8 times t. The velocity is given in terms of time, right? Then between 10 and 50 seconds, it's moving at a constant speed of 8, right? I think, what is this? Meter per second, right? And then after the 50 seconds, for the last 10 seconds from 50 to 60. So this is like the train journey in 1 minute then, right? The motion is described as v equal 48 minus 0.8 t. So if you're given this kind of information and you have to draw the graph now, and then you're going to find the distance between the stations. You don't have to draw the graph. You can actually do it by calculation. But I'm going to go the route of drawing the graph, right? So this is what the graph looks like coming there. It might not fit on this page. Oh yeah, it fits. It fits. Yeah, you can see it, right? But let's see how they get this graph. How on earth did they get this graph? So the thing says, the information says that from 0 to 10 seconds, right? The velocity is 0.8 t, right? So, okay, when t equals 0, if you put t equals 0 in here, v is going to be 0 because 0.8 by 0 is 0. So you know that it starts here, right? It starts here, 0, 0. Then at 10 seconds, 10 if you put 0.8 by 10, it'll give you 8, right? And that's how they got this point here. You connect these 2 points, and that's the velocity time graph for the first 10 seconds. Good. From 10 to 50 now, it's constant. It's constant, no acceleration. So down here, there's acceleration. Down here, no acceleration. It's at a constant speed. And then somebody seemed to yank the chain and the thing decelerates to 0. So you calculate that. Well, we know we're starting at 48, right? Sorry, it's at 8. So you want to know, well, all right, where will you end up now? Right? So look at this here. Well, really and truly, we're going to, so all we have to do now is kind of draw down from here to here. You don't need a calculation, really, right? You know that you are at 8, and within the next 10 seconds, that's from 50 to 60, you have to come to rest, right? The train has to come to rest. So you don't get scared by what's going on here, right? Good. So there is your velocity time graph. The distance traveled now is this area under here. This area under here. And there are several ways. This is a trapezium, right? This is a trapezium. And I think what you can do, there is a formula where when you have a trapezium, right? If this side is, let's say, A and this side is B, and the height of the trapezium is H, the area equal to half A plus B times H, right? Times H. You could put the H here too, no problem. So here, the distance travel will be equal to, you can do it what? Half of 10 to 50 will be what? 40? 40 plus the bottom there is 60 times 8, right? And maybe one of you can, somebody is burning
I got 400.
400, that's correct. 400 meters. Somebody is burning. I have a neighbor here, a youngster that is obsessed with fire. He's always burning something. Young boy. He's a clean freak too, I can tell you that. He's always chopping and weeding and getting rid of garbage, and he's always burning, and so good and bad. Alternatively, if you have trouble with this form and say, look, I ain't able with all this trapezium story, and you could take this thing in pieces. You could take this. Isn't this a triangle? Look here. This is a triangle. Find the area of a triangle. Then this is a rectangle. This is a rectangle. Find the area of that rectangle. And then there's another triangle, right? And you can find the area. And you add all of them up. And you will see you get the same 400. You'll get the same 400. You got that? So Erase all this again. Some reason I'm having some difficulty breathing in all this smoke. I think it's all of this caused my eyes to swell up. Because I'm near a window where there's some cold air coming in. And then there's smoke and it's causing you to rub the eyes and so. Okay, good. So lastly, you can have situations where your velocity time graph is not a nice straight line. It's not a straight line or it's not a trapezium. No, it might be a curve. It might be one ugly curve, right? You could have a situation like that, you know, and you might be called upon to find the acceleration, let's say at this point P. And again, to find the acceleration at this point, you would have to draw a tangent at that point. You know, a tangent. Tangent must barely touch it. Oh my. I struggle to draw on this graph. Right? So let's say this is the point P. You want to draw a line that touches this point P. Can't get it right. And find the gradient of that tangent, right? So you draw a tangent at that point. And if this point here is x1, y1, and down here is x2, y2, well, you know what to do, right? So your acceleration at P equal, again, the gradient, y2 minus y1 over x2 minus x1, right? Simple as that. If you want the average acceleration, well, things are going to be a little different. You'd have to draw a secant, and let me give you an example of that, maybe. So all right, I end up removing everything. Yeah, if I have like a curve like this and you want the average acceleration from here to here, maybe, you know, A to B. So you draw this secant line straight through A and B, right? Through here and through here. And this secant line, if the coordinates here of A is x1, y1, and the coordinates of B is x2, y2, then average acceleration is going to be the gradient of that, which is y2 minus y1 over x2 minus x1, right? The good thing is that you're doing this on a computer. And I have to give you the graph, I have to give you the line. Maybe you'd have to read off the point, though. You better know how to read a point, right? And then find the average acceleration, right? So much of the work, you end up putting it on me, right? So, yeah. Good. So with that, I think knowing the equations, how to apply them, and using the graphs, you should be able to solve problems that are of reasonable complexity, right? That involve displacement time, velocity time, and so, right? So you have all those equations, those motion equations, you have some knowledge of the graphs, right? And that can certainly help you. And your test is going to, well, it's only 10%. So how much can I test? Right? And we did so much, right? We did work on units. Remember we talked about units? We talked about units. We talked about not graphs, vectors. We went into kinematics. That's quite a bit. So I'll probably give you a couple of multiple choice, and some of the multiple choice you might have more than one. You have these ones where you tick the box, you know? You tick a box. And sometimes I make those difficult in that if you tick the wrong box, you lose something. Because sometimes some people wicked, they tick all the boxes. So they'll get all the right answer anyways. So sometimes what I do, I say, okay, if you tick the wrong box, you lose a quarter of a point. Right? So they can be tricky. And then there are multiple choice where just one is the answer. Right? Good. So come prepared. I'll give you some more information as we go along. But Tuesday evening, we might not have a class because to get through, remember you have to have this, what is it? Safe exam browser running and all of that. That does create havoc. So make sure you get your equipment ready. The computer must be in good order. You have the safe exam browser installed, working, internet, electricity, lots of things. Right? So we might spend the entire afternoon to run off the assessment. Good. So we will stop there. Right?
Sorry.